Okay, so today we're here at the very best session. I know you had a lot of competition turns, other sessions you could have gone to, but we're going to make sure that we don't talk about any code whatsoever this entire time. But don't be afraid, we're going to talk about models. So when you look at this picture, I hope you see something like a bunch of people building software, okay? And if that's as far as we go, that's as far as we take it, then a model that looks something like this for a software development process also makes sense, which is a very, very tight feedback loop that says, get some requirements, write a test case, because we're not animals, and then we edit the code so that the test passes, and then we refactor, and then repeat forever on into the future. It looks sunny, and we ride on horses, maybe unicorns, something like this, okay? But when I look at this model, I say, I don't see anything that differentiates us as software developers from someone planning a wedding or anything else that would require a fast iteration loop to resolve difficulty. So while I'm all for fast iteration loops, I say, where are the models in all of this? Because it's the models that we build in software that differentiate us from, say, mechanical engineers, or my brother William, who builds skyscrapers. So here are some examples of some kinds of models that I think everyone in this room knows about and we bring into the software that we build. There's a workshop going on domain-driven design. If I mention some design pattern names, that's going to trigger something in your head, and you've probably put that stuff in your code before. Of course, architectural styles, test-driven development is a style, different processes, these are also models. Okay? And we're bringing all those together, we're weaving them together every single time we write software. And so if we pretend those things aren't important, if we pretend that the only things that are important are the next requirement that we need to build, well, then every one of us as a developer is trying to sneak these things in despite this metronome that's beating all the time that makes it difficult to talk about those things, difficult to collaborate with engineers on these things. So I suggest something different, which is that modeling should be a first-class activity in everything that we're doing. Okay? Now, and honestly, if I'd said this 20 years ago, everyone would have been like, why? We can't possibly have a talk about this because everyone already agrees to this, okay? But I feel like through the years, we have gotten to the point that we have perhaps forgotten how important these things are. There's not a single other engineering discipline that thinks models are not a hugely important thing that allows them to do their work. We're not any different. So I want to differentiate the process I caricatured on the left, where you get a new requirement and you build some code and you repeat forever, with the one on the right. And the one on the right recognizes models as first-class things. And some requirements we get are really unchallenging. I have a UI, it's got 3 tabs on it. The requirement says make a 4th tab, maybe for sales or something like this. No problem, I've already done it 3 times. I know how to do it the 4th time, okay? Other times you get a requirement that's a real big challenge. So for example, maybe you have a client-server system set up, and then suddenly you need to have spontaneous things streaming from the server back into the client, okay? Like a ticker or something like this. That's different, okay? That's going to force me to reevaluate how I've built things. And the process that's caricatured on the right here is something that's closer to being able to reevaluate that, not just metronomically churn out new requirements. So to get to there, I would like to convince everyone in this room not just to have a gut feel, perhaps, that models are an interesting and important thing, but I want you to be with me and believe that they're an essential thing. So I've organized the talk into 3 sections. The first 2 are about theory building and then distributed cognition, which are probably terms that you're not familiar with, but we're going to chat about those. And then the third one is what we as software developers do that overcomes and is able to use the 2 at the beginning to get things done. So the first is theory building. Peter Nauer won a Turing Award, so I think we probably should listen to him. Here's the opening 2 sentences of an essay he wrote on theory building. Programming properly should be regarded as an activity by which the programmers form or achieve a certain kind of insight, a theory of the matters at hand. And then here comes the great sentence. This suggestion is in contrast to what appears to be a more common notion, that programming should be regarded as a production of a program and certain other texts. Okay? So he started this essay in a very bold way. He says, programming is about the understanding of the problem. It's not about the typing of the source code, okay? Now, many of you might be worried that you'll never get to go to another conference again if you show your boss this slide, right? Yeah, well, sometimes it gets a bigger laugh. I like that one. But in this particular one, it makes us realize that if there was a catastrophe, if all of our source code was lost and we were forced to build the program again, it would take a fraction of a time than it did the first time, right? Because it isn't about the typing, it's about getting the models all set up so that you can build the software. So in describing what it means to understand software, it evokes this philosopher from 1949 who was trying to explain what it means to understand something. Because I think we intuitively understand what it means to understand. Only philosophers can ask, do I understand understanding? But Ryle distinguished two different ideas. One is knowing that something is true. And so, as an example, when we all learned addition or multiplication when we were children, we have these tables, these memorized facts running through our heads even to today. And so I don't know about you guys, but there's still some part of my, 4 times 4, then 3 plus 3 is, whatever. And like at some point that stops. And it's like there's nothing running in my head that says 437 plus 252 is, right? There's no sort of memorized soundtrack for that. So Ryle distinguishes knowing that, which is a pile of facts that can be memorized, with knowing how, which is a generalized ability to do something. So in the case of addition, it would allow me to take any numbers and put them together. It would include the idea that when you take numbers and put them together, they get bigger. And when you subtract, when you take numbers, they get smaller. So it's that understanding that's distinct from having a bunch of facts at your disposal. So I believe that this is relevant when it comes to software because there's certainly a lot of facts that are relevant about a program. So for example, you might have a particular module that handles reporting. You might use certain technologies in your program, and you might have facts about how big it is, okay? But compare that with if you took the best developer on your project and you put them in front of a whiteboard and you start asking them questions. What happens? Well, they start sketching stuff out and they explain what goes on. And you say, would security be better or worse if I did the following thing? And they'd scratch their head and then they'd sketch some more and they'd tell you how this works. And you'd say, can you dig into this little part here? And they're like, sure, and they can dig right in, okay? And this is the kind of engineer that I'd like to be, one who actually understands why everything exists the way it is. I understand what stuff I hacked together last week and it's inelegant versus the stuff that I'm really happy and I think it's been working really well. Okay, so in terms of software development, I'm trying to do the thing on the right, which is I'm trying to build up these theories about how the software works and why it works. I think there's a metaphor here, a parallel with the way scientists operate. And this is a little bit of a caricature because as I understand, science doesn't progress in sort of the way that we're taught in school. But the basic idea of science, if I understand it correctly, is you make observations about the world. A lot of those observations are mundane. They fit the theories you already have. But sometimes you pick up an observation, one of these red dots, and you go, wow, that's surprising. That doesn't quite work right. And then at that point, you realize that your theory isn't sufficient to cover what you need. So over time, as a scientist, if I had a little pseudocode for them, their job is to make the observation match the theory. Right? Or rather, sorry, make the theory match the observation. So like, I don't want to be in a case where I pick up and see the world and then I go, wow, that doesn't make any sense. So imagine this in programming. This is the way I think of it, is that I've got little pseudocode that I run for myself, which is every time I get a new requirement, sometimes it's no big deal. And it's like, okay, I'd like another button on the such and such screen. Okay, da-da-da-da-da. I need you to respond to so-and-so messages on the server. Okay, da-da-da-da-da, I just do it. But every once in a while, they throw me a requirement that says, I didn't even know it was possible for customers to have 3 addresses. I didn't know it was possible to do such and such, right? So like the things that I built into the program are just not ready to handle that requirement. And it forces me to reevaluate things and I have to restructure my theories and models to accommodate. So as a software developer, I want to be in that situation as infrequently as possible, okay? I want to be looking at the requirements that are coming at me in a stream, and I want to have as few of those little red dots as I can coming at me. I'd like to be ready when they say, hey, are you ready to build this? And then the answer is yes. And if you go back and you read the original research or the original descriptions on technical debt, it's exactly this. It's saying like, what do you do in those situations where you hit a red dot and you don't stop the world, you identify it as technical debt, but you have to come back and fix it up, okay? He's not saying write bad code. He's saying, what do you do when the model in your head is in advance of the code that you've already written? So as it turns out, not every theory is as good as every other theory. Even the ones that work, like the geocentric model on the left, right? You could come up with ever increasingly complicated models to make things continue to work. And you may have showed up in a project at some point where the developers had built something like this on the left. And you look at it and you go, I can't believe this is going on. And then after a while, you become one of the people that's maintaining this thing going forward, because it becomes difficult to make an argument that says, now it's time to stop writing this crazy stuff, okay? What you're really looking for is a model that's on the right that's equally powerful, but it's suited to the environment, okay? It's suited to what's going on. It's simpler and better. So if you read the domain-driven design book, you may remember this paragraph. This one really struck me. In this, Eric Evans talks about the moment at which you're getting these new requirements from stakeholders and you're trying to rework your software so that the requirements work out. And then while complexity builds up, there can be this point of release where you go, oh, I get it, and your model starts to make sense and it fits together and you're like, okay, things are just clicking. And I saw a couple people nodding in the audience. Like when you experience that, you're like, that's what I need to be doing. And this is one of the reasons I'm giving this talk is if you look at the processes that we keep talking about, we don't talk about how that epiphany can ever happen and how that epiphany can be make its way into the source code. So going back to this quote, the second part of this hopefully makes a bit more sense here, is that the suggestion that we should be focusing on our theories is in contrast to this idea that programming should be regarded as the typing of programs, okay? So I've done a funny thing on the next slide, and I hope you appreciate it, which is that I've put these words in the mouth of the Dilbert boss. And you can imagine the Dilbert boss saying, okay, like, programming is the production of binaries which we ship into production. Like, what could be simpler than this, okay? And what you've got is me on the right-hand side saying, what I see in the world is a bunch of software developers, and if you don't give them the time to fix the snowball, every time you push out another feature, the snowball gets bigger and harder to push, and you have to hire more people behind it and the best people you can to push the snowball, right? And there is another way, which is if we give ourselves enough time to focus on the theories, then we are pushing a much smaller snowball much faster, right? And we don't let it build up as much. Easier said than done, but let's at least try to do it rather than just throw up our hands and just keep typing programs. So I'm saying, let's not do the thing on the left. Let's explicitly make model-driven design, program with models on the right. So when you look at your team the next time, and you see a bunch of people out there at their terminals typing source code, it's not that they're implementing features, it's actually that they're building theories. And I want you to think about that and say like, wow, look at all those people building theories about the world and putting them into software. The second part of the talk is about distributed cognition. Distributed cognition is a great magic trick. And if you've ever seen it before, this will be no big deal. But I don't think many of you have, and I think you'll enjoy this. So how many people can do this long division problem? It was what, 13,095 divided by 45. Is there anyone who feels comfortable to say that they cannot do this division problem? Okay. Is there anyone who can raise their hand? Because with an audience this size, there may be somebody who can do this in their head. Does anyone, feel comfortable doing this in their head? Like, no big deal. Okay? Well, okay. So maybe if we were in a very quiet room and you give me a couple minutes, like I could maybe get this done in my head. But it's clearly a cognitive overload kind of situation. And if I put more digits on these numbers, I stop being able to do it in my head. Okay? But if you give me a piece of paper and a pencil, I can just sort of grind it out like this, right? And there's no obvious point at which I can't just add more numbers and go through the process, right? This is kind of magic. And we've been doing it for so long, we forget how magic that is. I mean, just imagine you were in a society that had never invented this stuff, and you came in there and said, I can divide arbitrarily large numbers, as long as I have a piece of paper and a pencil. Suddenly, you have this superpower, right? You've just done a magic trick. Pretty cool, yeah? We do it every day, and yet it's pretty cool. So, distributed cognition is the idea that if you give me a piece of paper and a pencil, and you allow me to make scribbles on the piece of paper, I can amplify my cognitive abilities. And I do it every day. So it is so obvious that we don't even think about it. We're doing the same thing when we're programming. How many people can write a 10-line program accurately in your head? 1, 2, 3, 4, 5. Okay, we're in Germany. A lot of things can happen. Okay, pretty impressive engineering talent. Okay. How many people would collect their paychecks if all they could write were 10-line programs? I don't. 1. Okay, you work at a good. And you work for. Okay. Don't tell my boss. Yeah. So like this has got to be what's going on, right? Because if we can't write 10-line programs in our head, and yet the previous speaker talked about a couple 100,000 lines of code that they were refactoring, right? And it's not uncommon to have millions of lines of code that we productively work on. Clearly, the same sort of thing is going on, that like by writing the scribbles in our version control system allows us to work on things that are far bigger than we would otherwise imagine. Pretty cool trick. Okay. So it turns out it doesn't work for any scribbles. It's only certain scribbles. Can anyone do this problem? And you're like, ha, 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 nobody knows Roman numerals. I had to put this into Google anyway to figure it out. So it turns out, okay, fine. Arabic numerals only. Here you go. So what's wrong with that picture? It's the wrong scribbles. The digits are in the wrong place. The columns don't line up. I'm not ready to solve that problem, right? Okay. So as it turns out, this has been extensively studied, not long division, but this happens to be coming from the Stroop effect. And basically, if the model in your head is aligned with the external world, you get high performance, which is the bell curve on the left. And when the model in your head is misaligned with the world, you get low performance. And that's exactly what we would expect. So we got to get our scribbles right, otherwise this cognitive amplifier thing doesn't work. So a few minutes ago, you learned that you were doing a magic trick for the first time. And now I'm going to tell you, unfortunately, it's a very fragile magic trick, because if we don't make the right scribbles, it just doesn't work, and we don't get the cognitive multiplier that we would expect. So in this particular study, and this is the Donald Neumann who did the Design of Everyday Things book, if you guys know that one, what they did was they took a look at people performing a Towers of Hanoi test, where you like move the size disks across the columns, and a bunch of other equivalent problems which were actually the same problem in disguise, okay? And what they found out is that when people's ideas about what was going on were matched up in the world, compared to the equivalent problems, but that didn't match up in the world, that people had much worse performance. In other words, you could break their ability to solve the Towers of Hanoi by giving them the bad external representation, okay? So, you and your scribbles. Leave me alone, let me make scribbles, and ta-da, I get a magic trick. I can make whatever scribbles I want as long as they're the scribbles that work for my head. How many people only work by themselves in software development? Yeah, I mean, like we all work on teams, okay? So this is gonna get worse, because now I not only need to make scribbles that make sense for me, I need to make scribbles that work for the other person. Otherwise, the magic trick doesn't work. So imagine I was trying to do that long division problem, and instead I divided up each one of the little chunks of this and assigned it to a different person, okay? Now, I've been told by several Europeans that this is not even the way that you're taught to do this in school. Is that correct? It's like a slightly different sort of equivalent version of this. Now imagine you're on a team and you're like plugged in where it says Bob or Ann or something like this, and you're like, wait, no, that's not where it goes. And like, you know, we're like working across, it's like VI and Emacs or something, right? And it's like, you've changed the representation on me and I don't like it at all. So another thing that the psychologists have studied extensively is teamwork in the context of military operations, like steering of this Navy ship. And what they want to do is they want to figure out, how does this problem actually get solved by this team of people? Because if you think about it, like, wait a second, these guys all have to steer the ship. There's not like one guy steering the ship. Like, everybody is steering the ship. That's why they're all there. That's why there's not just one person on the deck. And you can see over here on this display that they've got an external representation of what's going on. What's more is that none of those people are sleep deprived. They all come into the bridge, they work, and they go back home, and then they tag off the job to somebody else, okay? So they've got these external representations. They've got this cognitively demanding task, which is steering the ship to where it's supposed to go, that they need that many people around in order to do. And they've got to successively do this over time and not screw up and not steer the ship in the wrong place and not forget where they were. Okay? So there's really two challenges going on here. It's the one we already talked about, this internal, external. Like when I look at the compass and I look at the charts and all that stuff, that it works and it makes sense and I get this cognitive amplification. Okay, so I got to get the internal, external matching. The second thing is that I have a problem because I'm on a team. No single person knows everything, so the knowledge is partitioned. And second is that we have to have a compatible external representation. So like when I see the chart and you see the chart, we both are seeing the same thing and it activates the same thing in our head. Okay, so I'm no longer allowed to make my own private scribbles. Has anyone wandered into somebody else's code and feel like they've seen some private scribbles that don't make sense to you? Yes, we all have. And other times we actually use an API and we're like, this API is wonderful. Like it took me a minute to understand what abstractions you want me to operate on, but like now that I've got it, makes perfect sense and I can get a lot of stuff done. I have this amplification. So we've experienced both of those two things. So I'm going to suggest that the way that we overcome these challenges is to do three things. We need good theories and models. We need good external representations of those models. And we need to make sure that the people on our team share the same model. And it's sort of like when I set it up this way, it all seems very obvious. But when you think about the processes that we often follow, it's not clear that any of these three things are being promoted as stuff that's critically important for a group of people. Think about this in physical terms. Imagine if our software was a physical machine sitting in this room. And like, this is not even that large of a software team. I mean, there's plenty of software teams that are hundreds of people, right? And that we're all coming up with our own desires, walking up the machine, pulling off a part, tinkering with it, putting it back on the machine, and like doing that all day long. Like how many check-ins are in your version control repository, right? And we're just doing that and it's gonna keep working. Like it's just amazing that that ever works, right? If you'd told somebody in the outside world that that's what we do in software development, they'd be like, it's never gonna work. And yet it does, right? So we must be using these models, we must be communicating these models, otherwise it wouldn't work. So where are we at this point? We talked about theory building. Theory building is the idea that there's a difference between understanding that and understanding how. And we're trying to achieve the understanding how. And that software development is really about understanding the how and building the theories about how our software is going to work. The second part we talked about was distributed cognition, that there's a magic trick that happens. If you let me have a piece of paper and a pencil, I can do things that are much bigger than my head. And that has to be happening in software development because I can't write a 10-line program in my head. I need the version control. So the third part of this talk is about what our theories and models are. I want to draw your attention to three primary categories of models. And you've heard about all these before. So there's not be like, ta-da! In section 3, I developed new models of software that shake the foundation of the world. It's not like that, okay? So many times when people think about modeling, and I need to do modeling on my project, they're thinking about the first column, which is the domain. Seems obvious. This includes the terms that your subject matter expert talks about. So if you are talking to your subject matter expert and you're talking about customers and accounts, that's domain modeling, okay? And there's a long history of this, starting in the Simula community in the late 60s, when they were doing modeling of, well, I think it was traffic control systems. And they said, look, why don't I just make the software represent the cars and the traffic lights in the streets? Okay, that seems to be perfectly straightforward. But there's nothing that says that has to be OO programming. I can do that in Lisp. I can do that in a functional programming language, okay? The second kind of model is the models of the thing that we design. Now, this is stuff that only software developers know about. If you go to your requirements person and say, I want to talk about a 3-tier system and I want to talk about microservices, they're not going to know what you're talking about, right? This is the discipline that we have as software developers. And this includes all the specific technologies that we use. So if you said, I express that in third normal form, nobody's going to know what that is except for software developers, right? These are all the particular models and theories that we have built up that help us do our job. The third category is one that we almost take for granted, and I have to admit, I wasn't paying attention to this when I started developing these ideas. But it's impossible to separate what we do as software developers from the mathematical foundations that we come from. The theories that anyone in the sciences would recognize, and in fact, a lot of philosophy pulls in this. So things like logic, set theory, category theory, and so forth, like you tend to treat them as libraries that you have in your system. But the critical thing is not there is a library. The critical thing is knowing that you need to represent your problem using that library. Okay? And that's not always obvious. And that's one of the things that I've been noticing happening with Java, with now that we've got more functional programming operators in there, is that you're seeing people not write out a for loop, right, that iterates through things. Instead, you now think about things as an operation, a mapping operation across a set, for example. So, 3 major categories of models. The pictures on the right are meant to call back to previous things in the talk here. The top one is that the ideas in my head and the ideas on paper must align. And the other one are, other two are, if I'm in a team context and if I'm doing software development, what I'm trying to do here is make all this magic work, okay? And what I need to do is I need to make the right scribbles on the piece of paper to keep the magic working. And I've got the 2 challenges still. I've got the internal, external challenge, and I got this team challenge, and I'm still trying to keep the magic working, okay? And it all seems very hard when I spell it out like this, even though we do it every day. So I'm gonna suggest, and maybe you guys are already 10 steps ahead of me on this one, that we gotta make sure that all 3 of these kinds of models are showing up in our code. So when I say, hey, show me the models in your code, and you show me customer and account, I'm like, great, you got 1 out of 3. Okay? If I can't see what architecture you're using, if I can't see that it's client server, or I can't see that there's a database layer, then there's probably a problem, right? If the developers on your team don't know that an architectural decision has been made, has everyone been in that situation where like somebody accidentally writes some code and then you find out, no, we don't do it that way, right? That's an example of they were not able to infer the model from reading the code. So we got to make sure those models are appearing in our code. And then finally, is the math and logic and friends, is that the functional programming community has been beating their drum sort of separately from the mainstream software development community, saying, you need to pay attention to math. And we've been all like, pshaw, we work with crazy requirements, we can't do that math stuff. And I think what's been going on maybe in the last 10 years is that we're realizing actually we can. There's a lot of our things that we're doing that are better expressed using a couple streaming operations and some mapping operations, and then maybe a reduction operation. You're like, once you get used to that, it dramatically simplifies what's going on, and it makes the math visible in your code that you were otherwise writing out explicitly. So, show all 3 models in your code. One other dimension I'd like to mention here is that a lot of times people tend to snap into one of 2 modes, where they think, I have to build models, or they think, I have to connect to models that are already in existence. And so I'm going to try to make that explicit and sort of tease it apart. In terms of the domain, has anyone ever worked with a standard ontology that someone has figured out, say for like, here's how accounting works, and you can just like look at a reference model? Yeah, that's a couple, maybe like 4 or 5 hands. That's sort of been my experience. It's like, I always hope, and I always go look to see if there is, because I say like, what is it called when you do this? And like, if somebody's already come up with a name for it, that's great. Okay, so that's the reusable stuff. But a lot of times it's just ask your subject matter expert, what do you call it when you go to the factory and you do the following thing? And they go, oh, we call it this. And you go, okay, great, I'm gonna call my class that, right? The solution, in the books, you're gonna find things like the design patterns book, you're gonna find architecture styles. But on the other hand, you're gonna come onto your team and you're gonna find out that they've got quirky different ways of doing things, right? So it's a combination of design knowledge that you get in books, design knowledge that you develop on your team. And then of course, math and logic and so forth, most of that stuff comes from books. I think you do occasionally find people actually inventing new formalisms. I'm thinking like in terms of graph theory, right? That you find like if you were doing certain domains, you might come up with your own algorithms or your own ways of navigating. So I implicitly mentioned this idea of linking between the things that exist in books and the things that exist in your source code. So there's this great story, a great debate actually. You guys have all heard about von Neumann architecture for computer systems, right? Okay. And so there's a great debate on this topic where these are the facts that are undisputed. He went in and sat down with a team of engineers who had built a working computer. Yay, we're engineers, we like working computers. They did not name the architecture after the people that wrote the code, built the computer. This is where the conflict comes in, because after he sat down with them, he got on a train, this is like from Washington, D.C. or Philadelphia, out to the west of the United States. And it turns out there was no internet on the train, and so he could sit there and concentrate. And what he did was, he took what he had learned and he took what he knew about logic and math, and he connected the two. And so he expressed the design of a software system in terms of models that people already understood. He linked the two together. So instead of there being a dozen people in a room who knew how a computer worked, you now had millions of people in the world who had access to the design because the two models had been linked. Okay? I think that's a pretty valuable thing. In fact, I'll go even farther and say that if you have a model and it only exists in a book, it's only really of academic interest. It's only when those models are linked to actual engineering artifacts, and then you can say, oh, I see why this thing works, not just that it works, that things go really well. And that is what I had when I was working with a friend at a startup company, and they were going for some financing, and they said, could you come on in and help me make this architecturally better, like the presentation of it? And so sure, and they drew this diagram, and it had, I don't know, 24 boxes and lines going everywhere. And at first I was like, I don't know what's going on. And eventually I'm looking at it and I'm like, I'm starting to see what's going on. And I was saying things like, looks like your system, broadly speaking, has the user interface, the logic, and the persistence. And they're like, yeah. And it's like they had no idea that anyone had ever recognized that pattern before, right? Like we were all there at one point, but that's where these guys were. And so I'm like, I think you have a 3-tier system. You might want to tell the investors you have a 3-tier system, okay? And then, they had some batch processing, and they had some stateless and not stateless stuff. Anyway, the point is that knowledge didn't come from nowhere. It came from the book, which happened to be my head or whatever. Like I'd remembered what was in the book, and I could help them link the actual machine that they were building with these theories, okay? So you got to link the theories that you learn about in your domain-driven design book, in your design patterns book, in your math books, link them to their code, link them to your code, make them visible so that when the other engineers on your team read that stuff, they go, I get it. It clicks and it works. One of the things that I wish I could do at this point in the talk is I'd like to come up with a great process for all of us to follow that would lead to the promised land where our code is linked to our models and it's always accurate and it works on all your projects, okay? No methodologist in the history of software development has ever been able to do this, although many have tried. Many have stood up here and have said, you should follow me to the promised land. And I can't do that because I've looked at that stuff and it just never works. Here's an example. I'm big into domain-driven design. I started programming in Smalltalk, for goodness sake, a long time ago. So yes, I like models and OO programming. So a few years ago, I was doing my first big data project. And we were using this Hadoop technology and this pig programming language. And it's a very limited language. And I'm trying to figure out how I can encode my domain in pig. And the answer is, you're not going to. It's just not going to happen. That language just doesn't support that level of operations. It's sort of like embedding your domain in your SQL statements, right? SQL doesn't give you that opportunity, okay? So the thing is, you're going to have to answer questions about are my models on my team only going to exist on the whiteboard? Can I just talk to the other developers? Do I write it in the source code? Do I name my variables this? How do I make my architecture models relevant? How do I make them visible to other people? These are great questions. If we don't figure them out, we run the risk of pushing the snowball and not actually improving the models. But there's no one-size-fits-all answer. Okay, so that's the whole talk. What I'm going to do now is show you slides you've already heard, because I feel like there's 3 big chunks of things, and I'd like to sort of stitch it together a little bit. The big idea is if we let our software process be too simple, be too generic, not specific for software development or even for engineering, then you can get something that looks like the left, where there's no space for models to get built. If you show up on Monday and you've got your stories to build, and by Friday they've got to be built, and there's not really an acknowledgement on your team that you need to sit there and you need to rework the models, then what you can get is just push the snowball another day. You can brute force things, and that's not what we want. I don't think it's what anybody wants. What I'd suggest is if we think about a model that looks more like the right-hand side, that it still preserves that fast feedback loop that we crave, that has given us so many benefits, but it allows in the door the fact that these models might need to be revised along the way, given the problem that I can't tell you exactly how to revise your models every time, right? But it's a great thing to bring up. The next thing is that instead of thinking about the work we need to do as little chunks of features that we add to the overall machine, we should instead be thinking about our understanding of the software as an integrated mesh of theories that we've woven together. It's a client-server system. It deals with accounts and customers. It's got this mathematical notation in the middle because I'm doing some functional programming. It's got like all this stuff woven together. And every once in a while, a new requirement shows up that is hard for that system to accomplish, and that we should be treating it as a refactoring opportunity rather than like, let's make that problem go away. That we are going to have two main challenges when we try to do this magic trick. The magic trick of distributed cognition. We have this problem that the external representation, like the scribbles on a piece of paper for doing long division, or in our case, the source code that we manipulate every single day, it has to be in the right format, otherwise the magic trick doesn't work. And we, like we said before, we all agreed and nodded our heads, we've read other people's code that is sort of inscrutable because that notation only really works for them. And the magic trick didn't work for us. And we got to figure out across our team, how do we communicate those models? Because when I come into the bridge of the ship and say it's time to start steering the ship, if I don't understand what's going on inside there, if I don't actually have the same models as everybody else, I'm not going to steer the ship very well. So we need good theories, we need good external representations, and we need to make sure everybody on the team understands what those are. We talked about 3 categories of models, and that all 3 should show up in your source code. The domain, which is the customers and the accounts and that kind of stuff. And I think everybody sort of has an intuition that they want to do that at these days. The solution, which is all that stuff that makes us software engineers specifically, all of those models that you read about. And then finally, don't forget about the math. So that's it. This is my talk on model-minded development. Hope you enjoyed it. Let's stop pushing the snowball. Thank you.
Thanks a lot. Are there any questions?
Yeah, first of all, thanks for the great talk. I enjoyed it. You talked about the times when modeling was pretty much common sense, and that somehow something happened that it's no longer the case. I wonder whether you have a theory about this. What's the reason?
I see what you did there.
Yeah, prepared that. 5 minutes. Yeah, and whether maybe the advance of Agile may have something to do with that, or whether this might be a coincidence.
So I think I was on the microphone. I don't need to repeat it, thank goodness. Okay, so here is my theory. And I'm going to, this is my theory from 1,000 feet away, because of course the story that we are engaged in over the past couple decades is as unique as every single person in their own quest to build good software. But in broad, horrible strokes, I believe here's what was going on, is that in the 70s and 80s, the software development field was looking at other mature engineering fields. They saw blueprints for bridges, they needed blueprints for software. What happened was, at the same time that we were developing sophisticated modeling representations for things, and sophisticated models of processes that would make sure that we were going to cover all the bases, right? So make sure there's a phase for testing. While we were doing all that stuff, we were also losing track of the fast feedback loops, okay? So it was like we were, while in an effort to address all these different risks and to put all the best technology into the process, things got slower and slower, and it was not unusual to have 8-9 month delivery windows. Like when I started software development, that's what we had. And I remember when I was starting to listen to the community that eventually became the Agile community, they said, hey, why don't you try doing little iterations? And people at work thought this was crazy, and I was still a young kid at the time. And so like this young kid was trying to say, I want to build software every 2 weeks and deploy it. And they're like, it's never going to work. And but they let me try it because they're foolish. And so I did, and what do you know? Making that one change, not changing anything else about the software development, in like 2 iterations, there was no chance we were ever going back. Okay, like after a month of software development, it stopped all the infighting, because what happened in about a month before deployment of this very long cycle, stakeholders would start throwing elbows at each other and just being very angry about, like, I need my feature in, otherwise I need to wait until next year before I get my features, right? And all that went away because they're like, I can wait 2 weeks. That's fine, okay? So so you can watch this sort of buildup of sophistication and technology, but it's unmaintainable because it's lost track of the fast feedback loops, because that's a great opportunity. So there was a break, and it was like a few trailblazers at the beginning, and it turned into like a much bigger revolution. And so, like with many things, there's a swing of the pendulum, right? And I think what you're starting to see, and from my experience, a little bit more in Europe than we're still seeing in the United States, but you guys, I'd love to chat with you afterwards. We're starting to see people go, wait a second, I still see value in these techniques that I had before, but I don't want to print out a binder of UML diagrams and put it on my shelf, right? Like, the two don't go together. So while there was a revolution and there was a lot of bad ideas burned out, it's now time for us to go and plant the trees and make the next forest that keeps the fast feedback loops, but doesn't let people tell us that we have just metronomes of build features like that. So that's my like super high level, completely inaccurate, but like maybe there's a kernel of truth in it theory of how that went. Thanks for the question. That was a good one. Yeah.
Okay, thank you. You can also ask through the app if you want to.
Thanks for the talk. So a little bit strange, maybe provocative question. So don't you think that some of the new languages that are being pop up like several years ago and being advertised quite heavily now, especially by Google? I'm talking about, for example, Go language, and not maybe the language itself, but the community, the whole message of the community is kind of step back from this point of view.
I 100%, I'm here of my own accord, speaking my own mind. I'm not speaking for my employer. That said, everyone who's at a company that has more than, say, a couple hundred people realizes there's pockets of different ideas, and there's active innovation within your company. And it doesn't mean that anyone's trying to make a consistent view of this whole thing, right? Like I could probably come up with public examples of Google where you'd say like, Google here is doing this and Google here is doing this and they're different. And I'm like, yes, that's what happens. Well, look, it's a login screen. Oh well, there's nothing interesting on there anyway. So yes, I would agree that this is an approach that I think a lot of the Agile community would be happy with in a way, right? You look at the technical debt literature and you see people trying to come up with a model of how things work and trying to make sure that model appears in the code. I think if you go to the architecture community, they would be very sympathetic with this. They'd say, yes, we've been trying to figure out what the right answer is about architecture being important, but you're talking about putting architecture in the languages? Yes, I think that sounds good too, right? And then of course the functional programming people, which at first I was having a hard time understanding because it felt like an orthogonal force to our software. I really realize it's just a different kind of model that we need to fold into there, and that once you embrace it, it took me a while, but like once I embrace it, I like can't go back, right? I'm like, I want to do OO and functional. I don't want to do one or the other. So yes, so this is not necessarily the C and Unix style large trend that's flowing through our history of software development, right? It's not that trend, right? It's much more aligned with the OO and other modeling trends you've seen.
Okay. Thanks.
You talked about representing the models with our scribbles, and our scribble is the source code. And in my experience, I often write code which I would like to view from different perspectives, and my solution often is to write different or draw different diagrams which are point out different aspects of the source code. And you spoke about the big folder with UML diagrams. Yeah. We need obviously something in between. Do you have some comments on that?
I think that in early days, say in the 80s, so-called case tools, and in the 90s too. Do you guys remember case tools, computer-aided software engineering tools? There was this idea that very much like CAD tools that my brother William uses, that if you're building a building, right, you can come up with one representation with a lot of different bits on it, and you can sort of slice through it any way you want. And you can say, show me the building, but only the heating ducts. Show me the building, but only the access ways. You know, show me the building, but just this part, okay? And when it comes to software development, there's been an effort to use the multiple views. Philippe Crustien's 4+1 paper from a long time ago, and in general, all of the literature from the SEI on software architecture embraces exactly what you said, that you need multiple views to call out certain things. Okay, all that's great, but here's the big problem. It's really hard to reconcile the three primary views of software design, which would be the source code that you type or anything else that you can tangibly see, the runtime of all those things, like if I can see here's my .class file, how many instances show up at runtime? Really hard to answer that question, right? Because you run into the halting problem of like, I need to analyze the program sufficiently well to know what's going to be. And then third, if I see some source code, which server is it deployed on? Like, believe it or not, that's actually getting far easier now that we have automated scripts for doing deployment. But like, if your company isn't there yet, or if you just go back a couple years, there's no way to tell where that source code is deployed. You literally have to go knock on Bob's and Ann's door and say, where did you deploy version 5 of the code? Because I'm seeing problems and I need to know what's going on, right? Like, that's the problem we face. So this model of, I want to dump it into a big CAD diagram and then slice it any way I want, has like actual computability problems, right? That I can't solve the halting problem, so I can't tell you, like, at this moment in time, these are the runtime instances. And so you end up having to do it sort of on your own because the software can't compute it for you. So yeah, so that's the problem we've been having, is that as software developers, we're drawn to those multiple views, but it ends up being on your whiteboard and in your head, and we haven't cracked the problem of how we get it into code. I am optimistic, actually, for the next generation of languages. There was a language called Arch Java, which actually put architectural constructs into Java. It hasn't been maintained. It was Jonathan Aldrich's thesis project. But I'm optimistic that if the kind of operations that you do, saying not just like I want to create an instance of this class, but this entire component, I want to like make large-scale things show up, and I have a language for doing that, that I then have the leverage that a tool might be able to use. The same thing with with deployability. If I have code that says take this stuff in version control repository version 5 and deploy it on server A, if I have code to do that, I stand a chance of actually building that case tool that can slice and dice through stuff. But without any code that I can analyze, and the closer that code is to declarative, like deploy the software every day at 3 o'clock, well, then it's easy to reason about what software is there. It's supposed to be there unless there's an error that says it's not there or something like that. Yeah.
There was a question in the back.
Would you say that the findings you found and the principles find a kind of implementation in clean code concepts?
Could you remind me of which clean code concept you're talking about? Because I have a feeling yes.
For example, how to name variables, how to model your models, and especially the parts or some of the parts you presented reminded me strongly to something that are stated in clean code and this universe.
Okay. Again, help me. Clean code, is that the Bob Martin stuff, the solid principles?
Exactly.
Okay, great. Yes. So yeah, absolutely yes. And I would also add into there, sleep over here so I can see you. I would also add in there, Kent Beck has 2 great books out. The first one you probably would never pick up. It's called Small Talk Best Practice Patterns. A friend of mine joked that he's going to make $1 million by calling it Java Best Practice Patterns and like just rewriting the source examples. Okay, but basically, Kent, if I remember the story right, he said, "I'm not writing any code until I have a pattern that explains why I just did that, whether I created a class or named a variable or whatnot." And the book was what came out of that. And one of the critical things that came out of the book was there was a pattern called intention revealing message name, okay? And he said, look, it's far better. He said, you're not writing the program for the computer. You're writing the program for the other developers who come back and say, like, what is going on here, okay? And so he was putting together a set of patterns by which he was creating code that could be understood by other people. And this is before XP, right? And so you can see how the lineage goes that XP says if you write code in a certain way, you minimize the amount of documentation you've got to write. And if you make sure that you're pair programming with other people, your models get communicated by verbal tradition, right? Not the binders full of UML, right? So you can see how these ideas play out in different ways. And you can imagine a team that was following XP practices could get away with a lower documentation burden and would express models in a different way.
Thank you.
Okay, so final question. How would I convince my boss to give me a pen?
Well, as it turns out, at this conference, I showed up here and I go, I forgot a pen again, and then boom, in the basket there were like 4 pens. But I think maybe the question was more metaphorical, like how do I convince people to do this stuff? So I can tell you an example. Hi, Owen, who was working with a coworker and saying, could you watch this talk? This is my buddy George. It's a 30-minute talk, and I'd love to chat with you about like doing this stuff inside our company. And apparently, the guy had it on in a window while he was programming. And I think, maybe not if English is your second language, but if English is your first language, you can watch these talks at 1.5, 2x. What he was really asking his friend for was 15 to 20 minutes of his time. Okay, and his friend wasn't willing to give him 15 to 20 minutes of his time. And so I would say, like, that's not a good place to start inside the company, as far as like convincing other people like that this might be interesting. So there's, I think it was Linda. I think it's our keynote. Linda Rising wrote a book about how to champion ideas inside of a company, because a lot of us as engineers sort of have this stubborn like, but I'm doing it the right way. Why is the stupid company not doing the right thing? And we're not really interested in championing change and like being a change agent and like winning over this guy, and then he's an influencer, and like all these kind of things that all the change books tell you have to do. Okay, so we're like poorly suited for that, but I think that's the right answer. As far as it's not a matter of giving you a pen, it's what you want is to be given the time to build the models, and then the opportunity to build a community, and then show that what you're doing actually works out. Or if it isn't working out, give yourself a chance to try out, to tweak the model and get better. Thank you.
Okay, thanks a lot.